Hello all, welcome to my YouTube channel. I'm Kaushik here. So, if you're following this metrics series, you are kind of aware that we are covering a lot of these topics one by one. So first we covered definition of metrics, then we saw addition, multiplication, spatial metrics, transpose metrics, inner and outer products, and all those things. Last session, I covered an abstract concept which is a vector space, and where we saw that um, set of vectors and a set of scalars can create a vector space. Today we will learn about the linear independence of vector. So today we will focus actually on linear independence. That means they are not dependent. Independence of vectors. So from the definition itself, we are kind of understanding that what we are talking. We are talking that the set of vectors consider probably a1, a2, and suppose an. These are all vectors, and all we are talking about uh, column vectors kind of thing right now, are linearly independent if um, if we um, do a constant, probably um, k1 a1 plus k2. These are all scalar values. Okay, k1 k2 are scalar values, and if you multiply them, kn an, this sum will be uh, 0. If this is 0, then we can say that it has only solution, that k1 equal to k2 and kn. Okay, and they all are 0. That's the basically a very, it's kind of a theory or theorem kind of a thing. So very important kind of a concept, that if the set of vectors are available in a vector space, and when we can say that they are linearly independent, that if we have some scalar values, and if we multiply those vectors by scalar values and add it, and if it is coming 0, then they are linearly independent, and for them as only solution is these values are all equal and 0. So what exactly its meaning is that no vector in the set can be written as a linear constructions of other vectors. No vectors can be written as a linear constructions of other vectors. So that's a very important line actually. So basically what we are trying to say, that you cannot construct another vector by linear combination of this a1 to an vectors. Okay, now let me show some examples so that it will be very easy. Okay, this is just, the theory looks like tough, but once you have some example, then it will be very easy. Okay, Let's say you have couple of vectors like 1 0 0, and probably b is 0 1 0, and you have another vector which is w, which is 2 3 0. Now just by seeing I can see that if we uh, make a linear combination with a scalar value, like if we multiply 2a plus 3b, it will form this actually, because 2a mean 1 0 0 plus 3b mean 0 1 sorry 0 1 0. Let me just erase it so that later when you see this documentation it will not be confusing. So this will be 0 1 0. So what does it mean? What will happen actually? So we'll basically 2 1 2, because 2 1 plus, so if you just want to see the complete step, so 0 plus 3 and 0 plus 0, so ultimately you are getting 2 3 0, right? So we can write w like this. So that's mean this is not linearly independent. So this is the conclusion from this, that these these three vectors, conclusion is a b w are not linearly independent. But whereas, let me use some another color so it will be easy to follow actually. But whereas if we form again same, a is same, um, 1 0 0, b is 0 1 0, and suppose we have another vector of 0 0 1, then it is um, it is basically linearly independent, because if you just um, multiply with any scalar value, let's consider any scalar value, let's consider a as a scalar value, and 1 0 0 plus b 0 1 0 plus c, and w is 0 0 1, this sum will be 0, because if you check properly, a b and c will come, and we know this will create a zero vector actually. So which concludes that okay, a equal to 0, b equal to 0, and c equal to 0. So we can say that okay, in this case a b and w, yes, that they are linearly linearly independent. So these are two very important concepts we learned today. One is the vector space, another is linear independence. So I'll say just try to understand with these examples, it will be clear. If this language are not clear, at least go by these examples, you will understand. Like these examples, it is not linearly independent because you can form this vector by this scalar multiplication and addition. But in this case, this is linearly independent. This set of vectors are linearly independent because you cannot form a linear combination, and if you try to form a linear combination, that will be 0, and in that case, because it's linearly independent, so it will be 0, and all the scalar values are actually 0. So that's the theory of this. Okay. um, Thank you so much for watching. Hope you like it. If you like, please hit the like button, subscribe, and see you in the next video. Thank you so much. Bye.